Here is some pretty difficult questions on the effects of special relativity that are going to involve Lorentz transformations because we've got a couple of different bodies and both traveling at different speeds over a given distance. Picture there is of the Parker Solar Probe, the fastest to date thing mankind has ever built. Kind of cool. All right, we've got two stars and they're separated by a distance of 4.8 light years. Between those stars is moving a spaceship and a space shuttle. So the spaceship has an observer on it, and that's labeled P. It's moving pretty damn quick at 0.78 the speed of light. And the space shuttle is still a little bit slower, but still ludicrously fast at 0.30 c. So the questions you have to figure out are question A, what is the maximum distance between the stars A and B that can be measured in any reference frame? What is the speed of shuttle S relative to P using Galilean relativity? Both straightforward questions. Then it starts getting tricky. Calculate the distance between star A and B relative to observer on the space station. Show the speed of shuttle S relative to observer P is approximately 0.6 c using special relativity. Calculate time according to observer P that space shuttle S takes to travel from A to B. Very tricky question. And lastly, state and explain the reference frame in which proper time for shuttle S to journey from A to B can be measured. I recommend pausing the video, having a stab at it. That's a good 10 minutes worth of questions at least. See how you get on. Right, here's the first couple of questions that we're going to go through. What we have is what is the maximum distance that the stars can be measured in any reference frame? So the effects of special relativity only make length contract, so that number is never going to get bigger. So in the inertial reference frame, if you were orbiting star A, just watching star B, light would still take 4.8 years to travel that distance. So the correct answer is just 4.8 light years. It's never going to get bigger. State the speed of shuttle S to observer P using Galilean relativity. So the equation for Galilean relativity is if you're on P and you're observing S, what would that look like? Here's the equation as in the data booklet. Now, if you were on P, you're traveling faster than S. So imagine sitting on P, watching S, it's going to appear to be going back away from you at the difference between your velocities. All right. So mathematically, you would be traveling at velocity v, observing the space shuttle S, which is at velocity u. So the difference is going to be 0.48. And because it asks for the speed, the minus symbol isn't really important and only really means that according to you, it's going to appear like the space shuttle is moving backwards. So that's what the minus symbol means. But yeah, you'd get away with plus or minus 0.48 because they've only asked about the speed, not the velocity. Right. Calculate the distance between star A and B relative to observer P. Now, we're not worried about the shuttle just now. We're only talking about the space station. And the space station is moving pretty damn quick at 0.78 the speed of light. So it's important we figure out the gamma factor here so we can work out the length contraction. So with a gamma factor, with the units here, we're keeping the velocities as ratios of the speed of light. So when I do the working for this here, you can see that I've just omitted c. So with that, that gives us a gamma factor of 1.59, which is two significant figures, 1.6. Now that we've got the gamma factor, what we need to do is use the equation for length contraction, which, oh, hang on, some animations going on here. Yeah, so the equation in the bottom right there, if we want to figure out the length that is observed, we take the proper length, 4.8 light years, divide it by the gamma factor, and that gives us 3 light years. Next up, we have a question asking about the speed of shuttle S relative to shuttle P as seen from the observer P. Here we go. So with the last 3 questions, the first one here, we are going to use the Lorentz transformation as from observer P being the inertial reference frame. So that would give us a velocity v of 0.78. So to figure out the speed of shuttle S using the Lorentz transformation, we would use this equation here. And because they're both going in the same speed, they're both going in the same direction, they're both positive numbers. And working all that through gives us an answer of minus 0.63 C. And that just means, still as per question, what was it? It was question B. It's still moving backwards relatively at 0.6 C. Okay, calculate the time according to observer P that the shuttle S takes to go from A to B. That's a confusing thing to think about just from itself, but it is a Lorentz transformation again because we've got two objects moving at relativistic velocity. So the equation in the data booklet gives us this. Now, the tricky part is you're considering the time that shuttle S takes. So if that was the inertial reference frame, the shuttle would be taking the distance of 4.8 light years traveling at 0.3 c. So there's our distance and there's our speed or velocity. So the time that would take would be 4.8 over 0.3 as your velocity. So that t here is going to be calculated as this t here. So that's the tricky part of this. We already know the gamma factor is 1.6. So here's our t here. And then after that, we're just substituting in the rest of the numbers to give us a final answer of 19.6 years. Which is the time it would take. So to 2 sig fig, that would round up to 20. Tricky question, that. Okay, state and explain the reference frame in which the proper time for the shuttle S to journey. So if it starts at star A and travels to star B, the proper time can only be measured from the shuttle's reference frame as it is there at both events, the start when it leaves star A and when it arrives at star B. There we go.